So the first thing I'm going to start out is giving an overview of the Wolfram Compiler. So the Wolfram Compiler is a way to compile Wolfram language programs, to translate Wolfram language programs that you might write into native machine code, the sort of lowest level of instructions that run on the machine. So it's combining a high-level language, Wolfram language, with very, very low-level execution technology. And it's also a very large-scale application of the Wolfram language. So I'm giving this talk, which is a broad brush overview of the compiler, not super technical, not going into lots of detail, and the detail that you can go into is very, very micro. So the idea of the compiler is to work with the Wolfram language. I'll just give a quick overview. Mathematica was released in 1988, and the initial focus was mathematical computation. And it has, like now, we've built up a steady set of features, many of which you'll be interested in or using, various symbolic and numerical computation and data analysis and machine learning and computational data and geospatial plots and computation and image and all the things that there's talks about many of these things going on today. But I'm interested in the programming language, and the Wolfram language programming has been traditionally a functional programming style, working with functions and passing functions around as first-class objects. And the execution has been via these Wolfram expressions, Mathematica expressions, that are rewritten and interpreted in an evaluator. I'm programming. There's a pattern matching system based on expressions, and a lot of function definitions work through pattern definition. And we've added over the years many specialized optimizations. And there's a core philosophy that we built into the system, not just into programming the whole system, of things such as automation. But some of the other things are, we think about tasks, not specific solutions. And that's actually there's sort of a power that itself, it seems very natural and obvious, but it forms a powerful form of abstraction. Or in computer science, you might think of that as polymorphism. So one thing can adapt depending on its input to solving different types of things, but there's some commonality to the whole thing. And we design components to interoperate. So we have this uniform expression structure. But we have this parser that creates a Wolfram expression, a tree structured object, and these expressions, they evaluate infinitely to a fixed point. And the whole system is typeless, which really means runtime typing. And it's also what you could call not a completely pure language. So there are side effects. You can assign values to symbols, and you can update symbols. So that makes it not totally pure. So the benefits of these expressions are that everything in the system, written as an expression, inherits behavior from that expression. So it has like a full form, which means it's serializable. It can be saved in and out of files or in a notebook. It's also easy to overload, modify, and customize, and lots of people do things like that. And the uniform structure means programs can work on diverse areas. We don't have a special language for manipulating graphics. We just use regular expression manipulation for that. But with this generality comes some challenges. So first of all, one big challenge is it's very easy to construct nonsense. I can compute a sine function of a Boolean. But, of course, nonsense is very subjective because there's probably some area of mathematics where that's incredibly important. But so it's a subjective thing. Depends what you want. But when you get these nonsense things arriving, they can start to compound and make confusing, hard to understand behaviors. And the behavior there is the thing I call everything means something, but not necessarily what you expected. Now, another consequence of that is it means it can be hard to verify things, and it can be hard to make efficient code. And as a consequence of that, traditionally, people have written a lot of the core system, or they want performant code, is not written in Wolfram language. So it might be prototyped in Wolfram language and then put in the internal code, or there's technologies like library link and math and WSTP and things that you use other languages. But despite that, there are many large, very large Wolfram language applications which can be written to be fast, and the Wolfram compiler is an example of such a thing. So the compiler for the Wolfram language, this is a long-term project that we've been working on for quite a few years, built in the Wolfram language. I'll show a little bit later how we actually do that. And it's like leveraging the latest in compiler knowledge and technology. First released in Mathematica 12 3 years ago. And we have big updates. It's very actively developed, every version. So the idea of the compiler, I'm just talking and I'll get into sort of examples and some more details in a bit. So we're converting Wolfram language code into native machine instructions. And it does this with what we call this JIT compilation system. And it can form a faster and sometimes very fast execution model for the Wolfram language. And it's also a nice implementation for the Wolfram language. Another thing that's quite unique in the compiler compared with any other sort of technology like that is that it sits very tightly and is very tightly coupled with the Wolfram language interpreter. And that itself offers, some quite unique opportunities. It can build standalone applications, and we've been enhancing it by compiling itself to make it run faster. So benefits were faster execution, you get a guarantee of correctness, not, much more than a regular Wolfram language program. If it compiles, it's probably going to do what you want, and it's probably, though not always, going to be beneficial. It fits nicely with other code generation system. It's a good way of leveraging external technologies, even going down to like GPUs, and I'll be showing some of that. So it's high-level language specification with low-level technology. So let's just dive in and do a compile. So here I have a function, and I give type annotations to the arguments, and I pass it into this thing called function compile. I get back this compiled code function, which I can, feed in arguments, and it gives a result. So I can do the same thing. I can give like an association of functions, and I get back an association of compiled code functions. And I can add some. So here I'm adding like an extension, a declaration of so I can build up a library, and I'll talk more about how to organize these things. This is a new thing in 13.2. And then I can pass this declaration into function compile, and it's calling the declaration. And there's a whole system of compiler environments and such like for adding and managing declarations. So what was my note here? So just to keep it, I'll show this a bit later, but here the interface to the compiler is by compiling a function object. But we've been adding in support for compiling functions written as like regular, colon equals with down values, and I'll be showing some of that, and that's been moving forwards. So here are some nice benefits that come out of the technology. So we are generating, the code generation is all done in memory. It's not leaving detritus of files and things that are loaded. When it compiles things, it's optimizing the code for this specific machine. So all of your machines are slightly different. You know, if you want the fastest machine, you have to buy a new one every week, and they're all slightly different. And when we build Mathematica that we ship out on a disk, we're building it for some sort of generic machine that by definition might be a slightly older machine. It might be missing some of the later technologies. So we can benefit from that in the compiler. And then another thing that we do is when we compile things, big programs, we're not linking things from a library, we're compiling everything. And this is enormously beneficial because it means you can start to merge functions. You get all sorts of cross-function optimizations and do all sorts of inlining of code. And once you start to do that, you can start to reach very optimal ways of executing things. So, a few other features of the compiler. It can detect errors and things. So this would be nice to go further with this. But for example, here, I've got a program and I've got a local variable and I've got a branch here. And in one branch, I'm initializing a variable, but I'm not in the other. This is probably an error. And actually the compiler rejects this. It says, value of X is not being assigned on all branches. So it's telling me this. And we've been working on, in a future version, nicer ways to actually show where in the function the error came. So that's uninitialized variables. Here's, our famous sign of a Boolean. So compiler doesn't know what sign of a Boolean is. You could add one if you wanted, but there isn't, it doesn't know. And so you get like an error about that. And so, this compiler, it's a new way to find unintended code. And it's a form of static analysis like Brenton's. And one of the things that I think would be interesting is to sort of combine the technologies. This is a form of static analysis based on type inferencing, and finding these errors early avoids the sort of cascade of runtime errors that can come up with. We also have runtime errors. So a common source of a runtime error, obviously it's much better to have compile time errors because then you can fix the thing. A runtime error might not be you that's experiencing it. It might be sometime later or something. But here's the common thing. So here I'm adding two integers together. So let's do this. And so this is kind of like the largest signed 64-bit integer, and I'm adding 0 to it. So that's fine. But when I add one more to it, it overflows the range of 64-bit integers and we get an error. Now, what in this particular case, the error gets caught and it re-evaluates the function in the interpreter. So we get this result here. Now, another interesting, kind of unique feature of the compiler is that it can it's generating machine code, but it can generate machine code for several platforms. So here, it's generating the optimized code for my Mac, but I've also generated code for a 64-bit Linux, Intel Linux, and an ARM 64-bit ARM Mac. And it's all packaged up in this compiled code function. And in fact, when you look at the compiled IR, we see this, and this is stored in a way that can be rehydrated very efficiently. So if I sent this compiled code function to one of these other types of machines, it would start working. But I created it on this one machine. And this is called cross-compilation. And it's a very streamlined way to compile things for different platforms. And this is actually very useful for our grid computing technology. So if you have people build these heterogeneous networks, and so this is pretty useful for that. So again, high-level Wolfram language integrated with low-level machine technology. And let's have a little look at kind of how this fits together. So again, I think this is like really, sort of a unique, interesting feature. So here we have the Wolfram interpreter, which has this one uniform data type, and the execution of functions takes place in the interpreter that might be calling internal code. Then we make a function call into compiled code. And in the compiled code, there are many types created by the compiler. One of those types itself is the expression that the interpreter uses. And in execution of functions is not in the interpreter, it's by machine instructions. So it's like the processor, you know, it takes instructions and executes them very fast. So this is a gigahertz computer. So this is at the nanosecond level. So in like a, you know, microsecond, it's doing thousands of instructions. So, and it's created dynamically by this technology called LLVM, and then computes the thing and it returns the result. So what's kind of interesting is that between the interpreter and the compiled code, there's a layer, an interface function. And what this does is it converts the mathematical expression into the actual type that's there. So when I marked up my function as taking a 64-bit integer, it converts the expression into a 64-bit integer, or it fails. If it's like not something that it can convert, that's a failure, but it won't do the wrong thing. And then when it's created a result, it converts the result back into an expression. And this code that sits in the middle itself is generated by the compiler, and you can add, there are ways of adding your own. So if you make your own types, you can add your own support for converting them into and out of expressions. And this makes a tremendously powerful workflow, because it means you can just do core things in the compiler, but work with them with other nice features of interpreted code. It also means, if you want to, that you can set up memory management and things like that. That's kind of useful. Just one last workflow things, and I'll talk about workflows a little bit later, but this is kind of a powerful thing. So you can have this workflow. So you have interpreted code, calls the compiler, and then the compiler itself can easily call some external library. So he had some nice examples, or it could be a library to do GPU programming and work with your graphics card, and then the results can come back. And so this gives a nice streamlined way to give dynamic scripting access to external libraries. So this is kind of powerful. Now, there's a type system for the compiler. The idea is there's very minimal markup. You might put some annotations on the arguments to functions, and there's an inferencing system that goes through figuring out how these flow through the thing. So it works. Sometimes you have to add sort of extra hints and things, and we've added a new function for adding hinting for type annotations, but usually I consider it a failure of the inferencer if you have to use those. But sometimes there are questions of decidability and such like. You can add new types, build things up, and we support, again, I'm getting this a bit more technical, what you might call the range of algebraic types, so product and sum types, and it supports function overloading in the type system. Now, I want to talk a little bit about how we support the Wolfram language in the compiler. So the goal is we want to support Wolfram language programs, and we have a program of things where we steadily add more and more support for this. But it's also the case that we don't support everything. So, and people say, oh, do you have a list somewhere of all the things that you support and you don't support? It's quite complicated to make that, because it depends what the arguments are and how you're using it. But I mean, and really the only real test is, is to try things, and you'll get errors if things are not supported. The compiler, one of the, value propositions about the compiler is it will never give a false positive. So if something compiles, that means it's supported. So, and obviously if it's not supported, it won't compile, but it won't say, oh, I know what to do with that. But in fact, it doesn't know what to do with it. That's not supposed to happen. To support Wolfram language, it's not just enough to have, I want to support, list-convolve and fold list and map and things. You also have to think about functions and the types that are being fed through those. And it's some combination of those that in the compiler team, we spend a lot of time to to design. For many users of Mathematica that are just wanting to use the compiler to make things faster, thinking about types is a bit harder to understand because you're only really working with expressions and you're only really thinking about functions. But you have to think a little bit about that when you're using the compiler. So what sort of support do we have? I mean, we've got, sort of a big collection of scalar types. Some of these are things that, I don't know if people are using numeric array, but these are things that might fit into numeric arrays, integers, reals, complex Booleans. And we work with these within obvious sort of functions. And some of the things we have are kind of, might be, so we support like quite large integers. So this is a thing, this is not a software variable sized integer. This is just an integer that's always 128 unsigned integer. It's always 128 bits. But sometimes for some applications, maybe number theory or cryptography or something, it might be quite useful to work with this. And the support we have is going to be extremely efficient for such things. So that's we have, in terms of array support, we've got pretty good support for packed and numeric arrays and also sparse array. So we work adding support for functions. So it's still compiling. This is ranked min. And actually we have quite good support. So I'm just showing how that might work. And just to show it's actually a little bit faster than so if I come here and I do ranked min, then I get back. So it's actually a little bit faster than the built-in thing. And actually for other types of ranked min that might be working with other types of arrays, it's actually very significantly faster because we've just got this nice polymorphic way of setting things up. So that's kind of a new thing that we've added. So here's working with arrays with functional constructs. So I'm doing fold over a packed array of reals and this thing here. So we get some nice, it gets the result. And this actually works. So here, let's just do comp data. And this works like that. This is the uncompiled function. And so we've got really quite a very significant speed acceleration here. And these functional constructs, they also work for numeric array, which is not supported in the evaluator. So there's better support for these arrays in compiled code. So there's another type of container that's the thing like packed arrays and numeric arrays are very good for numerical processing, but they're not very general. They can't be ragged, they have to be rectangular, and they can't work with general content. And to support this sort of thing, we made a thing called a list array that I'm going to demonstrate here. And so here I've got a function where I'm mapping over a list array, and it takes a little bit of time. The compiler is quite slow to execute, but the code it generates is quite fast. And when this comes back, there we go. And so it's quite, but it's very general. So I'm able to do sort of maps and things over lists and such like. So that's list vector. So this is a more general, so it can contain, things that can't go in packed arrays, and it can also work with, so here I'm got some ragged ragged data. So you could not make a packed array of this, but that's not a problem for a list vector. So it's kind of a bit more general. Another type is, we call this inert expression. This is the expression type that's used in the kernel, and it's equivalent to working in the internal layer. And this is how we work with things in the build support to interact with the compiler. So these things are very quick to compile, actually, because they don't do very much. And so here I'm constructing an expression. I have this inert expression thing applied to an argument. And so I can build expressions and do things and do other, programming constructs on them, such like. And this inert expression is the basis for another feature of the compiler where we can implement functions by calling back to an existing computation. And so some of the things like the subsets function, we can do this and get back. So if you have a list vector of machine integers, we can call subsets. This is working through the evaluator, but for subsets, actually, that's not really it's kind of a slightly expensive operation anyway. In addition to Wolfram language support, we have support for Wolfram language for the data structures, and these also work in compiled code. When we're working with the compiler, we have these compiler declarations. This is how we add functionality, and this is how we work in the compiler. And that's a nice thing because we're working on the compiler to build up the library the same way as users can. So it's not some secret internal thing. It's just some general way of doing it. And so here are some of the declarations that you can add. So we have a thing called, this is adding a function. So here I've added a function, it gets a name, and here's the type. So it's like takes two integers and it returns a Boolean, and there's the body of the function. We can also write what we call polymorphic functions. So these are functions where we haven't said what type this is. We're just giving a variable. So this would work for any other types. And I could give more constraints and restrictions on this that might help with overloading. We also have type declarations. And so here I'm declaring something a little bit like a struct. So this is one where the struct contains fixed types. And this is more like a polymorphic struct, a struct that contains itself. I haven't said what it contains. I've just said it contains something. And that can be useful. And then here's another type of declaration. This is one where I've said, find this function in this library, and this is the type of it. And then I can call that function. So that's some of the nice ways of doing this. Right. Working with the compiled code, the compiler, is quite slow to run, and we have a program to work on and improve this, but there's various ways of caching the result. So one key way of caching it is through the compiled code function itself. So I can take that compiled code function and I can sort of use it and paste it in, and it works just fine as a regular, as you might expect. So that's I could save this, I could email it to someone. It needs to be on the same platform, but you can also use the cross compilation feature, and then it'll work on different platforms. I can also export the function into a library. So instead of function compile, I'm function compiling it and then exporting to a library, and then I can load this library anytime and get back compiled code function. This has to be on the same platform. Now, we also have a way of packaging this up and saving things, compiled code, in a thing we call compiled components. So let's look at this working with down values. So here I've written a bunch of function declarations, and then I can sort of interact with these, you know, and it picks using the pattern matcher, it's selecting, you know, finds a particular pattern that matches, and then it returns the result. So I can work with this in the compiler. So one way of doing this is I can just say in my compiled code, I can say in my compiled code, I want, you know, to work with make a function from the down values of my fun, and it's got this type. And so I can make a function like that and compile this, and then I get the same, it's the same behavior, but what it's done when it does this is kind of nice, because what it's done is looked at the down values and it's built a function that has the same properties as the pattern matcher. So it's astonishingly faster. It's executing a function on the, you know, on the hardware of the CPU. It's not going through this complicated, very general pattern matcher. So we can do a little bit better. Might be useful is we could make a declaration. So here I've made a function declaration. In the compiler, it's called, this is the name in the compiler. This is the type, and it's saying the implementation is coming from the down values of this thing here. So I can make this declaration, and I can compile this. Works same sort of way. And again, the same sort of rules apply. I'm constructing a function for this thing. I'm constructing a function and compiling that function, and that function is going through the different, but it's a function that's unique to that set of down values. And then an even nicer workflow way that we've done is, you see here, I made a function, but it was just calling one thing. So you can actually elide, I can just say, you know, well, I just want to call this one function. And so that's an even simpler, neater workflow, and that works in the same way. Here's another example of doing this. So I've written a function like this. So this is a little bit like all true, and I can compile this, and that sort of runs like that. And then I could compile this function, and I'm working through the down values. So I make a declaration, and I can compile this, and it runs, which is all good. So very often with these things, you start to get tremendous speed advantages. So here I'm going to run the function. I'm doing it over 100,000, and that's the uncompiled version, and that's the compiled version. So this is sort of very significantly faster. So this is like 1,000 times faster. So that's quite nice. And it's even, you know, even if I go to the built-in all true, so that's a little bit faster. You know, it's like nearly half the speed of my top level, but it's still quite slow. Whereas the compiled version, where it sees all the code, it can inline things, it can build something that's very optimized, and that might be important for what you're doing. And so the right, I mean that's all pretty nice. So making these function declarations, especially working with down values, it is possible to work with developing things in top level and then trying to migrate bits or parts of your code into compiled code. And often it can run nice and fast, and also making polymorphic definitions. So a little bit of code can be used in multiple ways. And some of these things, I think if you wrote that previous thing in C++ or in Wolfram Compiler, it's a lot more work to make something in C++ like that. And it's very competitive, is in what we're doing. And what we're doing is nicely integrated into the into the rest of the Wolfram system. So a couple of other things we've written to try to help integrate with compiling existing Wolfram code. So these are things, Stephen showed some of these. So this is like, sometimes you need to have a branch, like something you can't quite figure out. There's a your evaluator way and your compiled way, they're slightly different. And we have this thing called if compiled. And so I've done if compiled, and this is the interpreted way. So it goes to this branch, and this is the compiled way, and it goes to the compiled branch. So that's a way of setting a different code path, depending whether you're compiled or not. And yet another useful thing is sometimes you want to work with like, regular down value code, but you need to add type annotations. And that's why we've added this thing called type hint. And the type hint, it evaporates. I'll just show you. See this, when you compile it, it's returning a 32-bit integer, you see. So that's, and when we evaluate it, it eliminates the type hint in the evaluator, but the compiler is making use of it. So this is a way of adding sort of, a little bit of help to the compiler, which sometimes is necessary. Right, compiled components. And this is a way to, to group or package up your compiled code. And it integrates very tightly with the Packlet system, but you don't have to use Packlets. So, and the components have a name, like Packlets have a name, and this provides a nice, convenient syntax for adding compiler declarations, functions, and types. There's easy setup and building and loading of libraries. You can install symbols that just point directly to compiled code, even faster than going through a compiled code function. And it's like a packaging system for the compiler. So we have built one with a link to a geographic geometry computing system. So here's the Packlet it lives in, and then we can load it, and we can see here the compiled component that's living in that Packlet. So we can extract that, and we can see it's got a bunch of declarations and installed functions and external libraries and useful function. And here I'm just going to open in, so this is not a nice 13.2 feature. We have line numbers. Isn't that great? So, and so here's a source file, a bit harder to see. I don't know if I can magnify it, but we have these. So here are the declarations, the type declarations. But I can just sprinkle these around in any order. I don't have to care where they are, and then they get sucked into the compiler if when it needs to use them. And it uses the Packlet system to locate these things, which is pretty nice. So declarations, there's a bunch of ways of working with these, but I can, for example, I could create a compiler environment, and I could say, when you create this compiler environment, add in these components. So it sort of builds that. And then once I've added that to a compiler environment, then I could do compilations using the declarations that have come out of this little thing that I've loaded. But you might also want to use to make a library, a thing, and this will invoke the compiler to build libraries that you could then, if I'm lucky, this is still a little bit, I can then load the library, and there we go. And it returns a bunch of, all these things that it's done. And then we can see a little demo of this. So we can initialize the thing, and then it's created all these symbols, definitions, but these are definitions that are coming from this geospatial computation thing. So, but it's created symbols, and they point directly to the implementation in the component. So just right, that's my thing of the components. So I'm just going to run through some workflows that we're trying to support. These are potential workflows that might be relevant to users, Wolfram users, Mathematica users. So one workflow, and this is one that might be relevant to quite a lot of people attending the conference, is just working with existing Wolfram code. So taking existing Wolfram code and making it faster. Now, one thing about this is it might not be the whole thing. It might just be bits of it where you're doing some sort of programming or iterating over some list of data or something. Maybe it's just those things, or you're selecting things, those things like that. Any true example, you might find that's something, and those sorts of things can be, applying functions to things can be quite beneficial. And you're probably going to use things like, certainly function compile, and if compiled type hint, down values function. You might use function declaration. You're probably not going to use type declaration. So another type of thing is to build entirely new functionality. You could build, like a sort of web server with this, entirely new functionality. So there'll be some prototyping and interpreted code, but essentially you're building code that could not run in an interpreted way. And you might be using function declaration, type declaration. You might well package and deliver what you've built with the component system. Another nice workflow, you might build a link. You've got some library, some C++ library that simulates the solar system for the next million years or whatever, and you want to integrate that into Wolfram language. Again, you could build a nice, very super efficient link to this using the things like function declaration and library function declaration, a little bit like that, exactly like that GEOS link. There's not a lot of programming that's been in that. It's just declaring things to adapt the library to be, called from Mathematica. And then yet another workflow, I think, is you could learn about compilers or research new techniques, maybe target fundamentally new technologies.